Today we're reviewing arithmetic combinations of functions and compositions of functions for 1.8. Arithmetic is an adjective meaning arithmetic, so we're going to add, subtract, multiply, divide. Okay, so for example 1, it says f of x equals x plus 2 and g of x equals 5x minus 3. Find f plus g of x. Okay, if they say f plus g of x, they just mean what is f of x plus g of x. Okay, so my answer is going to be in terms of x because x is still in the expression. Okay, so what is f of x is x plus 2. G of x is 5x minus 3. So if I simplify this, f plus g of x is equal to 6x minus 1. Okay, for the example B, I'm going to subtract the functions. So f minus g of x is the same as saying f of x minus g of x. You don't need to write this step every time, but that's all they're asking you to do. Okay, again, f of x is x plus 2. Then I'm going to subtract g of x. Since I'm subtracting the entire g of x, make sure you use parentheses. Otherwise, your signs will be off because you are subtracting the entire g of x. And then I'm just going to simplify the expression. My answer should be in terms of x because x is still written in the expression I'm trying to define. Is that negative 4x plus 5? Okay, so f minus g of x is equal to negative 4x plus 5. For C, I'm going to evaluate f minus g of 7. Okay, and I have two options here. Okay, one is I could change this to f of 7 minus g of 7 and then evaluate them each that way. Okay, let's see. F of 7 is, what's that, x plus 2, so 7 plus 2. G of 7, 5 times 7 minus 3. Okay, I'm going to go ahead and evaluate each of these quantities. So what is that? 9 minus 35 minus 3 is 32. Okay, and I would get negative 23 that way. Okay, the other way I could evaluate this, which would probably be faster in this particular case, is I've already figured out that f minus g of x is equal to negative 4x plus 5 because I just calculated that on part B. So I could just plug 7 into this expression. Negative 4 times 7 plus 5. I'll get negative 28 plus 5. I still get negative 23. It would have been a little bit less work. So both ways give you the same result. You can combine the function first and then evaluate, or you can evaluate each part and then find the result after. Okay, the last two operations are multiplication and division. So if I want to do f times g of x, I'm really just doing f of x times g of x, and I do want the x to remain in my answer. Okay, so f of x is x plus 2 times g of x is 5x minus 3. And then you do typically simplify this expression, so I actually want to have no parentheses or like terms. So I'm going to multiply this out. Okay, when I multiply f times g of x, my resulting expression is 5x to the second plus 7x minus 6. Okay, the last example is going to be, for arithmetic combinations, is going to be dividing them. So if I do f of x over g of x, let's see, f of x is x plus 2, g of x is 5x minus 3. This doesn't simplify, so this is a good expression, like just the way it is. Now, if they ask you to state the domain, that would actually be the harder part of this problem. Okay, this is an irrational expression, so there is a restriction on the domain. So there's more than one way to express it. The easy way would be all reals except for the value of x that will make the denominator 0, because I do not want 5x minus 3 to equal to 0, because then my fraction will be undefined. So x can't equal to 3/5. Okay, so all reals, x can't equal to 3/5. Okay, that's the easy way to write it. If you have that option, absolutely write it that way. Okay, if they ask you for interval notation for your domain, which your book often asks for, I want to include all the values from negative infinity to positive infinity, but I want to exclude 3/5. So to do that, I say I'm going to go from negative infinity not all the way to infinity because I need to exclude 3/5. So I'm going to stop and exclude 3/5 by using a parenthesis. And then I still want to include all the values higher than 3/5 to infinity. So this is really saying this is negative infinity to infinity, but I excluded the value at 3/5. The second topic in 1.8 is compositions of functions. The symbol for composition is that little open circle in between f and g. It's f composed with g of x, which really means f of g of x. The one thing to keep in mind when we are evaluating compositions is whatever that internal function is, you need to respect the domain of that inside function because that's where the x is getting plugged in first. So if that fails, it fails for the composed function as well as the g of x function. And when we get to one like that, I will show you. So for example 2, it says f of x equals 1 over x, and g of x equals 2x minus 5. For a, I'm going to evaluate f composed with g of 3, which is really f of g of 3. Okay? And when we evaluate this, we do whatever's in the parentheses first. So I'm going to evaluate the g of 3 first. Let's see, what is the answer to g of 3? Well, g is 2x minus 5. So if I do g of 3, and this one's easy enough, you could do it in your head. That's 6 minus 5, so I get 1. So I'm going to plug 1 here. F of g of 3 is the same as f of 1. Now I'm going to take the 1 and substitute it into the f function. The f function is 1 over x, so it's going to be 1 over 1. And that's going to evaluate to 1. So f composed with g of 3 is 1. Okay, for the next example, I'm going to do the same thing, except I'm going to keep an x in my answer. Okay, and then I am going to consider the domain afterwards. So f composed with g of x is f of g of x. Okay, now first I'm going to go check and see what's g of x. G of x is 2x minus 5. I'm going to keep the x in there because that's in the parentheses. Okay, now I'm going to take the 2x minus 5 and plug it into the f function where the x is. So now I have 1 over 2x minus 5. That's as simplified as it's going to get. That's a good answer the way it is. Okay, now the one thing is sometimes they will ask you to state the domain on something like this because there is a domain restriction on this. Okay, I'm going to show you how to do it using the typical equality notation, and then I'm going to use interval notation. Okay, so this is a rational function. So it is true the denominator cannot equal to 0. So I know 2x minus 5 can't equal to 0, which means that x can't equal to 5 over 2, and you probably do that in your head. So this could be all reals except 5 over 2, all reals, but x can't equal 5 over 2, something like that. Those are all acceptable answers. Okay, or if they do ask you to use interval notation, which this book often does, you want to show that it is all reals except 5 over 2, which means you want to show it goes from negative infinity to infinity, but I'm going to exclude 5 over 2. Okay, so I know it needs to start at negative infinity. I want to go into infinity, but I need to stop and exclude 5 over 2. So to exclude 5 over 2, I need to stop and put a parenthesis, because that means it cannot equal 5 over 2. It can equal everything lower than 5 over 2, but it can't equal 5 over 2. Okay, and then I'm going to continue because it can equal, x could equal anything higher than 5 over 2, but it still can't equal 5 over 2. So I use a parenthesis at the 5 over 2 to show that the 5 over 2 is excluded. And then I continue all the way to infinity. Okay, now I'm going to look back at the original function, because remember at the very beginning I told you if I do f of g of x, I need to respect the domain of that function on the inside. So at g of x, I had 2x minus 5. Now 2x minus 5 doesn't have any domain restrictions, so I don't need to go and take anything into account because the domain for 2x minus 5 is all reals. But I should always get in the habit of looking back and checking in case there is a domain restriction on that function that was plugged in. Okay, for example 3, f of x equals the square root of x, and g of x is equaling x squared minus 4, and I'm going to play with the compositions of this as well, and then check my domain. Okay, so f composed with g of x is f of g of x. So this is really f of, what is g of x? X squared minus 4. Okay, and then I'm going to plug x squared minus 4 into the f function, which gives me the square root of x squared minus 4. Now if I could simplify this, I would simplify this. But in this case, this is as simplified as it gets. Okay, now I do need to consider the domain restriction because there's a radical. And if there's a radical, there's pretty much always some kind of domain restriction if it's a square root or any other even root. Now this one's a little trickier because there's a squared inside the radical, so it's a little bit unclear as to what would make this less than 0. Okay, but I can at least think about what values would make this 0. Okay, well, if x squared minus 4 was equal to 0, I could add 4 and square root it. I could get x equals positive and negative 2. So at positive and negative 2, this is going to equal to 0. Okay, now I'm going to consider all the possible intervals which are valid. Okay, it's possible that all the numbers lower than negative 2 are valid for this radical. It's possible that the numbers between negative 2 and 2 are valid. And it's possible that the numbers 2 and higher are valid for this particular radical. It's not clear which ones are going to work unless you learned at your school another way to check them. So I'm going to kind of check each interval and see which ones work. So let me first consider this first interval, negative infinity to negative 2. I'm going to pick a number that's between negative infinity and negative 2. Let's plug in negative 3, because if negative 3 works, everything in this interval will work. Now if I plug negative 3 into here, I get negative 3 squared is positive 9. 9 minus 4 is 5. Can I square root 5? I can square root 5. It's irrational, but I can square root it. Okay, now I'm going to go to the next interval and see if this interval works. Okay, do the numbers between negative 2 and 2 work? Let me pick an easy number between negative 2 and 2. I'm going to pick 0, but you could check any number. Okay, if I plug 0 into this function, 0 squared minus 4 is negative 4. If I try to square root negative 4, I'm going to get an imaginary solution. So that's going to be an invalid member of the domain. Okay, now the last interval I should check are all the numbers higher than 2. Okay, maybe I'll plug in 3. If I plug in 3, 3 squared is 9, 9 minus 4 is 5. I can square root 5, it's irrational, but there's nothing wrong with it. Okay, so there's 2 different intervals that work for this function. One is from negative infinity to negative 2, and it can equal negative 2 because 4 minus 4 is 0, I can square root 0. Then if I also plug in the numbers that are greater or equal to 2, those also work for this particular function. Okay, after I did all that work, I am going to double check my composition because I need to respect the domain of this inner function. So g of x is x squared minus 4. That has no domain restriction, so I don't need to add any more restrictions to my function. Okay, now let's consider g of f of x. Okay, now f of x is the inner function. So what is f of x? F of x is root x. Okay, so now I'm going to take the root x and plug it into x squared minus 4. So that's root x squared minus 4, which is going to give me, though the squared and the square root cancel, so I get x minus 4. So the composition of g and f turns into x minus 4, which is a pretty nice answer. Okay, now if I consider the domain on this function, x minus 4 has no restriction. It seems like it should be all reals. So let's go with the thought of all reals, but then I'm going to check, because I need to check this inner function here and respect its domain. So what is f of x? F of x is square root of x. Square root of x, does that have a domain restriction? It does have a domain restriction because it's a radical. If it's a radical, x has to be greater or equal to 0 in order to plug it in. Okay, I need to respect this restriction and add that to the domain of my composition. So even though I thought the domain was all reals, it's actually all reals, only x is greater or equal to 0. Because if I can't plug a negative into the original function, the f of x function, then I can't plug it into the composition. Okay, to write this as interval notation, the domain, I want to show its x is greater or equal to 0, so it can equal 0, and it can extend to positive infinity. Okay, the last example in this section, they kind of want you to play with decomposing a function. So they tell you that this function h of x is composed of 2 functions, f of g of x, and they want you to think about what possible functions could this be. Okay, and there's many, many ways to do this, so it takes some creativity for you to think about it. I'm going to do the first one's a little bit straightforward, and then we'll try the next one a couple ways. Okay, so I have to think about what I'm doing, because I want to think I'm doing f of g of x. So I'm going to start with g of x, and then I'm going to do something to it. So it looks like I have 2x minus 5, and then I am squaring it. So one possible decomposition would be, okay, I started with 2x minus 5, and then what did I do to my 2x minus 5? I squared it. So I took whatever it was and then I squared it. And then if you think of f of g of x, if I take the 2x minus 5 and I plug it in x squared, it gives me the h of x result. This is not the only solution. There's just a billion, million, infinite number of possibilities for decomposition. Where are they having you do this? Because in calculus, sometimes it's easier to analyze a function if you can decompose it. Okay, I'm going to try the next one, and I'll show a couple ways to do it. Okay, you kind of got to start it and think, like, what did they do to this? Okay, one would be they started with like an x plus 2 maybe. Okay, let me think. If I start with an x plus 2, what do I do with the x plus 2 in order to turn it into h of x? Okay, well, what do I need? The x plus 2, I need to square it and put it at the bottom, and then I need to put a 3 at the top. Okay, that's one possible decomposition. Are there others? Yes, there's millions. If you're creative enough, you could really game this system and think of a million. Okay, it could also be, if I'm thinking of an easy example, maybe I just started with x plus 2 squared. Okay, and then if I did f of g of x, what do I do to the g of x in order to turn it into 3 over x plus 2 squared? Okay, well, it's already x plus 2 squared, so I just need to put it at the bottom and put a 3 at the top. And then this could be another possible decomposition, but again, there's millions of other ones you could also think of if you really would like to be creative.